Hello, I'm Sophia Lemons, and I'm here to talk about triangle search and anytime beam search. This is work that I've done in collaboration with Carlos Linares Lopez, Rob Holte, and Wheeler Rummel. Today I want to present you a new anytime approach based on breadth-first search rather than best-first search. It has a simple design and easy implementation, and shows strong empirical performance. First, I want to talk about beam search. Beam search is a satisficing heuristic search, which can be viewed as a restricted breadth-first search. It's restricted because it limits the number of nodes that can be selected and expanded to some fixed amount per level called the beam width. In the example I'll show you here, we're using a beam search with width 2. At the first level, the root level, we have only the root node to expand. When we expand it in this example, we see that it has 2 children. Because our beam width is 2, we're allowed to select both of these 2 children and expand them. When we expand them, we see that there are 4 children now from both of those 2 nodes, and we select among those 4 children. We select the best 2, by the criteria that we're ordering our nodes on, and we discard the others. When we select and expand those 2, we see that they also have 4 children, and we would select and expand the best 2 among those 4 children as well. And the search would continue onward until either a solution is found or until it runs out of possible plans to pursue down the paths that it's attempted. This limited view of the search space often allows beam search to solve problems that are too large to be solved by other, more comprehensive approaches. Triangle search also deals in depth levels of the search space. In this example shown here, we've expanded the root and we put its children into a priority queue, which is called open 1, and they are at depth 1 here. We select the best among them and expand it. We've called that node A here. When A is expanded, its children are put into a new priority queue for depth level 2, which we've called open 2. Then that iteration is complete. So we begin again at depth level 1, selecting another child of the root from open 1. Here we call that node B. When we have selected and expanded B, its children will be added to open 2. However, now we are allowed to deepen by 1 depth level further than the previous search did. So on this iteration, we expand a node from open 2, which we call D here. Its children are inserted into a new open list for depth level 3 called open 3. Then this second iteration is complete. So we return to depth level 1. If any children of the root node remain, then we would select and expand them. Here we call that third node C. Its children are inserted into open 2, and then 1 more node is selected and expanded from open 2. We call that E here. When E is expanded, its children are inserted into open 3, and the best among the current nodes in open 3 is selected, again deepening our search by 1 depth level, selecting and expanding the node F. The search would continue in this way, beginning at depth level 1 and iterating downward, increasing by 1 depth level further than the previous iteration. This allows the search to both widen and deepen simultaneously. One important thing to note is the ancestry of nodes when they're selected by triangle search is limited because of the order in which things have been selected and expanded from the previous levels. While we know that A, B, and C are all direct children of the root, D, for example, could only be a child of A or B, because these were the only nodes that had previously been expanded at depth 1 and their children inserted into open 2 at the time that D was selected. Whereas E could be a child of A, B, or C, and F could be a child of either node D or E, which means that it could be a descendant of nodes A, B, or C. This allows us to follow paths downward in new iterations if the new nodes that we have expanded at the higher levels have children which are better than what we had available before, but we retain the nodes that were previously on that depth level's open list to select from them if they turn out to be the better ones. Some details on search ordering for triangle search. First, in non-unit cost settings, it was shown in previous work that beam search algorithms, which use f of n, meaning the incurred cost so far, g of n, plus the estimated cost to go, h of n, tend to perform poorly. For that reason, we use d of n, the estimated distance to the goal, to select nodes to expand at each level, instead of h of n, the estimated cost to go. We are still able to retain completeness and convergence to an optimal solution. We do that by storing the best solution that's been seen so far as an incumbent. We're able to discard nodes that have an f value greater than the cost of the current incumbent. And we continue search until there are no nodes at any depth level with f of n less than the cost of the current incumbent. We also present the slope parameter, which allows Triangle to add more than one depth level at each iteration, while still expanding only a single node at each depth level as it iterates downward. In the example shown here, Triangle used a slope of 2 and has performed 2 total iterations. In the first iteration, at depth 1, node A was selected and expanded, and then at depth level 2, node C was selected and expanded. The search therefore added 2 new depth levels at that first iteration. On the second iteration, it begins again at depth level 1, selecting and expanding node B. Then at depth level 2, it selects and expands node D, and now moves into adding 2 additional depth levels, 3 and 4, selecting and expanding nodes E and F at those levels respectively. This allows us to adjust the balance between deepening and broadening in triangle search. We tested triangle search against several modern other anytime algorithms on a variety of domains: the sliding tile puzzle, the pancake problem, blocks world, and vacuum world. In each of these settings, we tried a variety of sizes of problems, cost models, and action models. The experiments were run on a 2.6 gigahertz Intel Xeon machine, with each algorithm being given a memory limit of 7.5 gigabytes and a time limit of 5 minutes per instance run. All algorithms were implemented in a C++ framework, which can expand approximately 1.5 million nodes per second. We compared triangle search to 2 other top anytime algorithms, Anytime EES and ARA star. With ARA star, we tested 3 different configurations of the weight schedules available to it. First, here we see coverage in the 24 puzzle sliding tile domain, where the number of instances solved, in other words, coverage, is plotted against the x-axis of time on a log scale of seconds. We see that early into the solving time, Triangle begins to give competitive coverage with the other algorithms, and then the number of instances which it is solved quickly rises above the other algorithms, and Triangle reaches full coverage before the other algorithms. We saw this fast solving time in all of the tiles, domain sizes, and cost models, and both of the blocks world action models. We also show solution quality, where quality is the cost of the best known solution, optimal where available, divided by the cost of the current incumbent solution. Therefore, a quality of 1 would mean that an algorithm returned the best known solution, either optimal where known or the best among all of the algorithms tested for all of the times they were running in our setting. We see that triangle again begins to give good comparable quality to the other algorithms early into the solving time. It rises above them in terms of quality, meaning that it is both solving problems and giving good costs of solutions fairly early on, and stays above the other algorithms until the end of the time provided to the algorithms for solving. Triangle again gave this best quality of solutions in the tiles problems and the blocks problems that were tested. In the pancake problem, Triangle, with its default configuration of adding a single depth level at each iteration, was slower to begin solving problems. Its coverage is 0 until well after the ARA star variants have completed solving all of the problems, and then it does, once it begins solving some problems, quickly reach full coverage. However, this is not desirable for an anytime algorithm. We did find, however, that increasing the slope parameter, adding more depth levels per iteration, provided faster solving for triangle in the pancake problem setting. When triangle was given a slope value of 500, it started solving before any of the other algorithms and reached full coverage at about the same time as the ARA star configurations. So adjusting the slope in the pancake problem gave us fastest solving among the algorithms tested. And likewise for quality, adjusting the slope to a higher value gave us higher quality than all of the other algorithms for the vast majority of the time period at which the algorithms were solving problems. In the vacuum problems, we saw again that triangle was lagging behind in its solving time. It did not begin to get coverage until later than the other algorithms and did not reach full coverage until after the other algorithms. And unfortunately, increasing the slope gave some improvement, but not significant enough improvement to outperform the other algorithms in this setting. So this had an impact on the quality of solution that triangle could provide in those settings. Before it solves, its quality is, of course, 0. Once its quality begins to rise, once it begins to solve problems, it is giving good solution costs comparable to the other algorithms. And in fact, by the end of the solving time, triangle, with both of its parameter settings here, was giving better quality solutions than the other algorithms. This is, however, a significant weak point for triangle search, which we are addressing in future work. Stay tuned for future developments. The other comparison we did was triangle search with fixed width beam searches, seeing if triangle could provide that guarantee of completeness and convergence to optimality while still solving quickly like beam searches and hopefully with comparable solution quality at the times that beam searches would have solved the problems. And we saw for most of the problems tested and the times that the search algorithms were running, that triangle search in fact did give comparable quality to the best configurations of beam search in those problems. So what we've seen today is a new depth-based anytime algorithm, triangle search, which often outperforms the top current anytime algorithms, and can give competitive performance with fixed width beam searches in which the best beam value has already been chosen. Triangle is a simple algorithm, easy to implement, that can be competitive with other anytime algorithms. Thank you.